we've been kind of limited in the type of data that we can look at with the z-table and the t-distribution, and even sort of squeezing proportions into this, because we know that sometimes group data can be interesting. And we're kind of limited by just comparing two groups when we do those difference of means tests. Well, what if we had a situation where we wanted to compare multiple groups and see if there's a difference between them? So we got to go a little bit away from our comfort zone and do something called a chi-square. Now, chi is a Greek letter. What's it look like? Greeks in the house? It's an X. Mathematically, it looks kind of like a cursive X. And you put the 2 next to it, it's chi-squared. The handout that I gave you shows what the distribution looked like. And what does it look like? What's this look like? Yeah, it kind of looks normal-ish, right? There's a hump. But it looks skewed. Right? It looks like it's skewed in this direction. Right? Where you have much more volume of cases, much more area on this side of the middle. Sorry, with this tail coming out this side of the middle over here, right? So there's a lot more area out here. Well, there's actually a reason for that. The reason that it looks skewed is because of the square, because it's chi-squared. What happens when you have a negative number and you square it? It becomes positive. So what is our distribution going to start at? Yeah. And it can only get positive, right? It can only get a positive number because of the square. So there's more out here in the tail because, well, we've squared it. Okay. How does this work? Right? Mathematically, how does it work? Well, let's start with this example. Right? Let's say you have a group of people and you're going to classify them according to a personality type. Alpha, betas, gammas, and deltas. So your alphas are extroverted and norm favoring. Your betas are introverted and norm favoring. Your gammas are extroverted and norm questioning. And your deltas are those people that never leave their dorm room. They're introverted and norm questioning. They never leave their dorm room and they don't take a shower. Okay. So you have these 4 personality types. And if we classify people according to these types, we notice there we go, that there are a lot more alphas and gammas than there are betas and deltas. Now, what we have here is we have a sample. So we have to ask ourselves, how close does our sample distribution represent the population distribution? Right? How different is it? The chi-square is designed to test the difference between what we observe and what we would expect to observe, our expectations. Now, if you've heard that word expectations, when else do we set up our expectations when we're doing statistics? How so, Jake? Well, okay, you said some things that are right, but some things that were wrong. So you said hypothesis testing, and I liked that. And then I said how, and you said, well, null hypothesis, and I like that. But when we craft a null hypothesis, how do we do so? Well, all right, we assume that there's no connection between or difference between the groups, right? So an assumption could also be called a expectation, right? So maybe our null hypothesis could be that alpha, beta, gamma, and delta are all equally distributed in the population. Wouldn't that be a null hypothesis? That they're all the same? Okay. So our expectations can come from previous theory or research. So we can build in our expectations. I'm going to caution you against this, though. Right? And revert more towards the idea of equal distributions in categories. We've kind of already done this, right? Because when we assume about a gender gap and we set up a null hypothesis, what do we usually assume? That men and women think the same. So the only wrinkle here is that we can have multiple groups. So how do you do this? Well, you're likely to do a chi-squared in the form of a table. So instead of an equation, you're going to build a table. You're going to have each of your types, the frequency that you observe. Put a big old O in there. Right? The frequency that was observed. Now, let's think about this for a second. I observe that there are more alphas and gammas than betas and deltas. But what do I expect? I expect that they're all the same. So how could I create, if I wanted to, a category of what I expect? How do I figure out what number to put in there? Okay, I have a total number of 588 students. And I have how many groups? 4. 588 divided by 4 is 147. Okay. So I have my frequency observed, my frequency expected. In order to construct the chi-square, couple of steps. Easy math. Okay? First thing you do is you take the difference between the two. The difference between frequency observed and frequency expected. Should it matter which one you subtract from the other? It should, but it won't, because what do we think we're going to do to it? We're probably going to square it. But just for the sake of, doing it right, FO minus FE so now we have a difference. But if we were to add these numbers up, the 104 minus 82 plus 47 minus 69, what would we get? We'd get 0. Have you seen this before? When in statistics have when we added differences up, you get zeros? Also, when we do the standard deviation, what are you subtracting? When you subtract the observation from the mean, so x minus x bar, you get a number. And then if you were just to add those all up, they'd add up to 0, because that's what the mean does. Well, our expected frequency is sort of like a mean. Because it's this total number among this groups. Something tells me that if you were to add up these numbers and divide by 4, oh wait, yeah, that is the mean. Okay? So another way of, well, I just wrote. There, you can see that. All right. So frequency observed minus frequency expected. Next step, square it. Okay. Last step. So far we're up to here. The last thing to do is divide that by frequency expected. Okay. So you're going to go back to this table and divide these all by 147. Okay. Then the last thing is to sum them up. So looking at that equation again, your chi-square statistic is the sum for each of the observations of the difference squared divided by what is expected. This isn't hard, right? The math, still not hard. Right? You have an equation, you follow it, you set up your table with each of your categories, observed, and then you set up a column with expected. You take the difference, you square it, you divide it by what's expected, and then you sum that column up. That gives you a chi-squared. That gives you a test statistic. So let's take a look at the table that I gave you, the chi-square distribution table. Okay. I picked this one out. Why? Picture at the top. Right? So we have our distribution. It starts at 0. I guess theoretically you would be able to get a chi-squared of 0 when what would happen? What would it take to get a chi-squared of 0? Yeah. So what you observe would have to be what you expect, because then there would be no difference between them. So if you perfectly get what you expect, you would have a chi-squared of 0. All right. So the way that this works is, for each chi-square, right, you're going to determine what your critical area is. So where are you going to reject? Where are we, as political and social sciences, most likely to look for an area of rejection? 95%, okay? So I got to have, well, it's this column here. Oh, I can't write on this. It's this column with the 0.05. This is going to be the column we look for. Unless we're told otherwise, this is the column that we're interested in. We have our old friend degree of freedom here. And this one that I gave you, it goes up to 100. Okay. If you have a situation where you're sort of in between, let's say your degrees of freedom is 55, and you're not sure whether to use the number for 50 or 60, I usually say round, so you could sort of round up to 60. That way you won't falsely reject a null hypothesis that you should have accepted, or not accepted, but not rejected. Okay? So that's how these work. So let's go back to our example from the book. Here we go. How many groups did we have? Well, we had 4 personality groups. We're calculating one statistic, the degree, right? We're calculating the chi-square, so we're going to subtract one statistic, and we're going to use a degree of freedom of 3. So 3 degrees of freedom for 0.050. So 3 down from 0.05, 7.815. That's our magic number. If our chi-square is greater than 7.815, what do we have? We would reject the null. That what? Not that everyone's the same, but that the size of the groups are the same. Okay. So the chi-squared for this example was 166.74. Is that greater than 7? Yeah. So our chi-squared of 166.74 is greater than, remember the alligator always eats the bigger thing, 7.81. Therefore, that's what the 3 dots stand for, therefore, we reject the null hypothesis at the 0.05 level. Let's go back to the table real quick. Okay, 166.74. Is there any, let's see, this is getting smaller. Yeah, we're way, way small. Okay, so the probability that you would get these differences when in fact the groups are equally sized is really, really small, right? Because the degree of freedom of 12, or right, 12.8. Our chi-square is 160. So if we were to get the actual probability, there would be lots of zeros before we got a real number. That's how small the likelihood is. Okay. So again, at the 0.05 level, we're looking for a 7.8. Even at the 0.01 level, we would be looking for an 1134. and we're way out here. All right, we're well in the rejection zone to reject the null. And that's chi-squared.